Have you ever looked at the chaotic web of wires inside your devices and wondered how engineers actually make sense of it all? Well, welcome to this explainer. If you're a college engineering student staring down your very first circuit analysis course, I want you to take a deep, relaxing breath. Today, we're setting a completely low-pressure tone for mastering your electrical fundamentals. We're going to look through some incredibly helpful materials, ranging from dense textbook pages to just beautifully clear, handwritten student notes, all to transform the way you see electrical engineering. We are absolutely not here for a high-stress lecture. Instead, we're just going to walk through these core concepts calmly and logically. Okay, let's just dive right into this. When you open a formal electrical engineering textbook for the very first time and you see a dense network circuit diagram like this, you know, the ones with multiple loops, independent voltage sources, dependent sources, resistors everywhere, it is completely normal to feel a wave of overwhelm. I mean, your brain sees this tangled web of lines and symbols and it instantly thinks, there is no way, this is way too complex, where do I even begin? I want to validate that feeling for a second. It does look chaotic, but remember, literally every complex structure in the world is just a combination of very simple, understandable pieces. So how do we actually make sense of this chaos? Well, the secret is surprisingly simple. We don't need to memorize the chaos at all. Actually, scratch that. We just need to learn a few basic building blocks to decode it. Once you understand the fundamental rules and the individual pieces that make up these diagrams, you'll have the tools to unravel absolutely any circuit placed in front of you. It becomes way less about agonizing over the whole giant puzzle and more about just, placing one piece at a time. To get us there, here is our reassuring roadmap for today. 1. The invisible foundation. 2. Mapping the circuit playground. 3. The rules of the road. And 4. Simplifying complex networks. Let's get started. Section 1. The invisible foundation. We're talking about charge, current, and voltage. Now, charge is beautifully simple. It's just a characteristic property of a particle. That is literally it. As noted in the handwritten student sources we're referencing, protons have a positive charge, electrons have a negative charge, and neutrons, well, they have no charge. This intrinsic property is measured in a unit called coulombs. It is the fundamental root of everything we're going to discuss today. Because honestly, without charge, there is no electricity. Once we know what charge is, we can talk about electric current, which is usually represented by the letter I. And listen, current is absolutely nothing to fear. As defined in our source materials, it's simply the rate of flow of electric charge over time. Just think of it as the speed and volume at which those tiny charges, specifically the electrons, are traveling through a conductor. To put it in perspective, if 1 coulomb of charge is transferred in 1 single second, you have 1 ampere of current. It's just tracking the movement of our invisible foundation. But, those charges don't just move on their own, right? They need a push. And that brings us to electrical potential, which is way more commonly known to us as voltage. According to our source notes, voltage is defined as the amount of work done to move a unit positive charge from one place to another. So think of it as the necessary effort, the pressure or the push required to get that current moving through the circuit. Without voltage, the charges just sit there doing nothing. With voltage, the current flows. Moving on to Section 2, mapping the circuit playground. Let's look at active and passive elements. We can categorize our network elements neatly into 2 main camps, active and passive. Active elements are the components that actually supply energy to the circuit. They're the engines driving the whole thing. Your independent and dependent voltage sources and your current sources, they live right here. On the flip side, we have passive elements. These components do not supply energy. Instead, they either dissipate it or store it. This includes things like your resistors, which dissipate energy, and your inductors and capacitors, which store it up. Seeing a peer break down these network elements into active and passive, or linear and nonlinear, really grounds these classifications. It totally strips away the intimidation factor of a printed textbook. When you see a resistor drawn with just a simple jagged line and pen, it reminds you that a passive element is really just a physical piece of material designed to resist the flow of current. It's a highly logical, completely structured playground. All right, Section 3, the rules of the road, Ohm's and Kirchhoff's laws. So the most famous rule, and really the fundamental bridge connecting our 3 core concepts, is Ohm's law. It states that at a constant temperature, the current passing through a conductor is directly proportional to the voltage across it. This gives us the incredibly famous equation, V equals I times R, or voltage equals current times resistance. It just elegantly ties together the push, the flow, and the physical passive element resisting that flow. But here's the thing. Ohm's law alone isn't quite enough for complex networks. We need some traffic laws. Let's look at the handwritten logic for Kirchhoff's laws. First up is Kirchhoff's current law, or KCL, which tells us that the algebraic sum of the currents meeting at a node is equal to 0. Simply put, whatever current enters a junction absolutely must leave it. Second is Kirchhoff's voltage law, or KVL. This states that the algebraic sum of voltages around any closed circuit loop has to be 0. The total voltage supplied perfectly equals the total voltage dropped across the passive elements. They really are literal traffic laws. What goes in must come out, and every journey around a loop has to account for all the energy given and taken.
Now, to apply these traffic laws, we have to define the physical spaces where they actually operate. From our source nodes, we clearly see these definitions. A node is simply an interconnection of two or more branches. A branch is a direct path joining two nodes. And a closed path, or a loop, is a path that starts and arrives at the very same point without crossing a node twice. By identifying these spaces on your schematic, you're basically giving yourself a spatial map to safely apply Kirchhoff's laws without getting lost.
And finally, Section 4, Simplifying Complex Networks, Superposition and Star Delta. Let's start with the superposition theorem. Our textbook source defines it beautifully. An element or circuit obeys the principle of superposition if the net effect of the sum of causes equals the sum of their individual effects. Okay, so what does this actually mean for you? Well, it means if a circuit has multiple power sources, making it look totally chaotic, you can untangle that massive problem just by looking at one power source at a time. You just turn the others off, short-circuiting your voltage sources and open-circuiting your current sources, and solve the simple circuit. Then you just add up your results. It's an absolute game changer. A brilliant way to turn one really hard problem into a few very easy ones.
Another incredible tool is the star-delta transformation. And listen, this isn't just some neat math trick for your exam. This is actually how the world gets its power. When you look at large-scale power grids, engineers use three-phase transformer connections to efficiently transmit electricity over incredibly long distances. These transformers are literally wired in either a star, also known as a Y configuration, or a delta configuration. So when you're calmly converting a stubborn delta circuit into a manageable star shape on paper, you're actually learning the fundamental math that connects your city's power grid. It's a fantastic real-world application that also lets you easily apply standard series parallel rules.
Comparing the formal typeset textbook star-delta conversion diagram directly to a student's handwritten equivalent proves something pretty vital. The math is exactly the same. The dense textbook version is completely within your grasp because a peer, sitting in the exact same college lectures as you, was able to boil it down into clear, simple pen strokes. And that brings us to the core realization of our journey today. Every complex grid, no matter how intimidating it looks at first glance, is really just a sum of simple rules. A massive circuit is just a collection of basic charges being pushed by voltage, flowing as current through active and passive elements, politely following Ohm's and Kirchhoff's traffic laws. There is literally no circuit too complex once you break it down into its basic building blocks. So, as we wrap up this explainer, I want to leave you with a peaceful, reflective question. Next time you open your textbook and look at a tangled circuit diagram, instead of feeling overwhelmed, which simple building block will you choose to identify first? Will you look for the nodes? Will you trace the active voltage sources? By applying this structured clarity to your next study session, you completely take the chaos out of the equation. Thank you so much for joining me, and happy studying.